Assalamu alaikum everyone, this is me Ali Sudesh. I am a computational chemist. I am CEO of Ali Coaching Academy, Ahmedabad. I am a motivational speaker and I am ETA instructor. Last time we started the video lecture of computational chemistry in which I just gave you an overview of computational chemistry. What we're going to do today, we're going to talk about computational chemistry. What is computational chemistry? What is theoretical chemistry? What is the difference between these two chemistries? How theoretical chemistry helps out the computational chemistry and how the computational chemistry helps out the experimental chemistry. So we will talk about the relationships between these three chemistries. Like these three, they are dependent on each other. Okay, and then we're going to talk about some of the scope of the computational chemistry, that what is the scope of computational chemistry in the recent modern era. Okay, do you remember when we were in colleges, the chemistry teacher, they were bringing the sticks and the plastic balls to make us understand those chemical models. Like they were bringing the sticks and models, they were making like CH4 and ethane and different kind of models and molecules to make us understand the properties and the structure of that compound. Nowadays, the same modeling is carried out in computers. The computational chemists, what they do, they create and they do the modeling like those teachers were doing with those plastic balls and those sticks. The chemists, especially the chemists, were doing those computations for centuries, but it wasn't called a different field. Before, maybe you remember or not, but there was a theoretical work in which the ozone splitting or decomposition was studied and the formation was studied. But finally, in 1975, I guess, three scientists were there and they worked. When they worked, they laid the foundation for the powerful program and that are used to understand and predict chemical processes. You know who they were? Their names were, there were three scientists. So you can see there were three scientists, three chemists actually. One is Martin Karplus, Michael Levitt and Ari Warshall. They worked and they showed to the world that actually the computer models mirroring real life have become crucial for most made in chemistry today. Like in chemistry, they have done so much advanced works via computer that the real life, like the things doing, they mirror it. Mirror mean, for example, you want to do an experimental work. That work can be done through computer. If you want to synthesize something, you can synthesize something, that thing model through computer. You can know about the reaction mechanism via computers. You can know about the starting point, how to find the starting point. So these are the three scientists. I told you, the three scientists, Martin Karplus, Michael Levitt and Ari Warshall. These are three scientists who got the Nobel Prize in Chemistry in 2013. So therefore, the Nobel Prize in Chemistry, which awarded and due to for work for the development of multi-scale models for complex systems. So those complex chemical systems were used via computers. So therefore, they became unique. They became very different. They played very different role, very unique role. And after that, chemistry was called, the computational chemistry was considered as a different field. And now computational chemistry is a complete different field of chemistry. You know what? Computational chemists' daily work influences our understanding of the way the world works. They help manufacturers design more productive and efficient processes. Like before, you were doing the work in the lab, you were doing day and night and months and years, and after that you got to know that this work is possible or not. But now the computational chemists, what they do, they help you out to manufacture. They help you out to design the new compound. They help you out to design the new drug. Okay, they characterize new compounds and materials. Like when you were using a lot of money and those were so much expensive. But now the computational chemistry has made everything so much easy and they help other researchers extract useful knowledge from mountains of data. So what is computational chemistry? You know what? Computational chemistry actually relies on the results of theoretical chemistry and computer science. Like the theoretical chemistry and computer science, these two are necessary for the computational chemist. Like if you don't know about the computation, I mean you don't know about the computer programs, or you don't know about the chemistry, these two are very important. If you don't know about either of these two, it means you can't be a good chemist, computational chemist. If you want to be a very computational chemist, you must know about the computers, and you must know about that specific field of the chemistry. So the theoretical chemistry is actually the mathematical description of chemistry. It is development of algorithms and computer programs to predict chemical properties. For computational chemists, this is not the job of computational chemists. Keep remember, the development of algorithms and computer programs for those chemical processes, this is the job of a theoretical chemist. Okay, what the computational chemistry is? Computational chemistry is the application of already existing computer programs and methodologies, and they use for that specific chemical problems. Got it? What the theoretical chemists do? The theoretical chemists, they develop the new processes, they develop the new computer programs, and the computational chemist, the computational chemist come and he uses or she uses the already existing programs. It means this is the application of the theoretical chemistry. So practice of efficient computer calculation to obtain chemical and physical properties of molecules, liquids and solids. Okay, so computational chemistry actually has two main aspects, two different aspects, and those aspects are very important. Number one, for example, you have an already existing experimental data. Now the experimental data is used by the computational chemist, or the computational studies can be carried out to find a starting point for a laboratory synthesis. So if you want to do the synthesis, what the computational chemist can do, he can do the calculations and he can tell you that what is the starting point for that. Or for example, if you have that experimental data, so the computational chemist can assist to in understanding experimental data, such as like position and source of spectroscopic peaks. Okay, the computational studies can be used in the second different aspect and different way, and that is the first way we talked about, that if you have an experimental data already, so if you have the experimental data, the computational chemist can help you out in two ways. Like if you want to synthesize in the advance, he will help you, and the second, you have the experimental data, he can assist you to understand the experimental data. Number two is you don't have any data, you don't have nothing with you. The computational studies can be used or can be carried out to predict possibility of so far that entirely unknown molecules. Okay, or it can explore the reaction mechanism that are not readily studied by experimental means. So we talked about this in the second aspect, the two things. Number one is there is a molecule, the molecule which is not already present in the world, in the universe, and what he does, the computational chemist, he predicts the possibility of that compound, number one. And number second thing is there is not readily there is no reaction mechanism which is explained by the experimental chemist. So the computational chemist comes and he tells you that how the reaction mechanism will be. So he explores the reaction mechanism. So thus computational chemistry can assist the experimental chemist. He can assist, help out the experimental chemist, or he can do the second thing, and that is to challenge the experimental chemist to find entirely new chemical objects. For example, I'm telling you there is a fullerene. The fullerenes were first were studied by and explored by the computational chemists, and later on, like you can study, there are four kind of Ln, Lp, Bn, Bp. So you will find some of those fullerenes were made later on, were synthesized later on when it was studied by a computational chemist. Okay, so therefore computational chemistry is very, very much important for the experimental chemist. Like a time is coming when the experimental chemist will 100% use the computational chemistry. They will do work together, or he will learn the computational chemistry. So let me just define in an easy way that computational chemistry use mathematical approximations in computer programs to obtain results related to chemical problems. Okay, and computational quantum chemistry, there are two kind of. So computational quantum chemistry focuses specifically on equations and approximations derived from the postulate of quantum mechanics. So it solves the Schrödinger equation. Schrödinger, we call it Schrödinger. Some people call it Schrödinger. So Schrödinger equation for molecular systems. Ab initio quantum chemistry so uses methods that do not include any empirical parameters or experimental data. So there are two chemists, there are two kind of chemists exist in, one is called computational chemist and the other is theoretical chemist. So the computational chemist use existing computer software, like Gaussian is present nowadays, ADF is present nowadays, and a lot of other softwares are present nowadays, and most of them are commercial to study problems for chemistry. So if you want to solve that problem for chemistry, you will use a software, so that is an already existing computer program or software. And what the theoretical chemists do, the theoretical chemists, they develop new computational methods and algorithms. So what is computational science? Computational science simulates structures and properties numerically, we call it mathematically, based in full or in part on the fundamental laws of physics. Got it? It means that computational science, it tells you about the structure and their properties mathematically in mathematical way, and it uses the fundamental laws of the physics. Okay, so computational chemistry is also used to study the fundamental properties of atoms, molecules, chemical reactions using quantum mechanics and thermodynamics. So therefore, computational chemistry can be used for the atoms, molecules, reactions and chemical reactions using quantum mechanics and thermodynamics. Okay. Now, in theoretical chemistry and computational chemistry, there are two very basic tools. We call it two fundamental tools. And the first thing is you need a modern computer, like you need very computer which has high-speed supercomputer, and you need a cluster. Like many computers have been they have been arranged together and they are attached with each other. That is called a cluster. So you need a cluster nowadays, because if you have a large compound, large number of atoms are present in there, then you can't use the small system. So therefore you need a very big system, and the suitable software program is needed. Like there are a lot of softwares nowadays, but these are the two fundamental. If you have a very good computer and you have very good software, you can do a very good computational chemistry, or you can do a very good theoretical chemistry. Keep remember, computational and theoretical chemistry is actually the application of mathematics, physics and computer sciences. It is the application of these three fields like physics, math and computer science, and they are used to solve the chemical problems. Okay, so there are some of the softwares which are used in computational chemistry. APOD, its name is abbreviated profile of drugs. Abbreviated profile of drug. The drug is there, so this is used for drug discovery, not drug design, drug discovery. And ADF is there, the Amsterdam density functional package. So this is a little famous nowadays, and this is used for the first principle electronic structure calculations, a first principle embedding theory that combines the salient features of DFT and traditional quantum chemistry. So the traditional quantum chemical methods are used with the DFT, and it gives you the calculations. So therefore it is a little bit famous nowadays. It is used for the heterogeneous and homogeneous catalysis. It is used for the inorganic chemistry. It is used for the the heavy element chemistry, various types of spectroscopy, and also biochemistry. Then there is ADME. ADME works DDI simulator, and this is a software application for the risk of potential drug-drug interaction, allowing the user to perform both quantitative simulation of competitive and mechanism-based inhibitor. AMBER is also used in there, which is a molecular dynamic use. In the last lecture we talked about the AMBER very shortly. AMSOL is there, which is a semi-empirical quantum chemistry program, which is used for the gas phase and solvation, these two. APBS is a program which is adaptive Poisson Boltzmann solver, and this is software for evaluating the electrostatic properties of nanoscale biomolecular system. Argus Lab 3.0 molecular modeling software, BioSolve IT, software solutions for structure and ligand-based molecular design. Chemicine is there, which is a quantum chemistry program for visualizing electrons, spin density distribution, and UV visible spectra, plotting molecular orbital energy level diagram, and calculating atomic orbital populations, contributing of atoms and fragments of molecular orbitals. Cosmologic is also software, which is also a life sciences and chemical engineers use that software. And GAMIS is also there. GAMIS is also a ab initio program. GRUMAX is there, which is also an MD software. Liquid Crystal is there, which is an MS Windows based application, covers all aspects of liquid crystal research, material properties, display technologies, theory, basic research and applications. As you know, liquid crystal is used in the display, so therefore when we study the display we use the liquid crystal. MDL QSAR, which is comprehensive QSAR modeling system. I will tell you what QSAR later on in the after 6, 8 or 9 lectures. MOLCAS is there, which is quantum chemistry software package. Polar is there, which is electrochemical simulation and data analysis. QChem is, you know, the Q, you know the Q is there, so the Q and CHEM. So QChem is ab initio and DFT molecular modeling package, uses the quantum chemistry. Schrodinger is there, which is computational chemistry software. SIGRIS is there. SIGRIS is a unique desktop molecular modeling software package that can apply a wide range of computational models in all type of molecular system, from small organic molecules to bigger ones. These are some of the software I told you. It is not important that only these softwares are present. There are a lot of other softwares as well, but we will talk mostly about the Gaussian 09, because I have done all Gaussian 09 or Gaussian 16, mean 16. I have done work before in Gaussian 09. Now I work on Gaussian 16, so I will tell you all the processes and how the Gauss view computational chemistry is okay. Computational chemistry is rapidly growing field in chemistry. This is a very rapidly growing. There are two reasons. The one is computers are getting faster and algorithms and programs are maturing. And you know that this is the need of the day. Computational chemistry is really the need of the day, because if you work in if you work experimentally in the lab and you do all these works, you need a lot of time. Those are very expensive in terms of time and in terms of money and in terms of many other things as well. So therefore some properties, this computational chemistry is very important. There are some of the properties that can be calculated with computational chemistry. Number first is electronic structure simulations, geometry optimization. I told you in the last lecture that when you want to do some calculation computationally, the very first point is that you optimize that structure. So the optimization studies are very, very much important. And equilibrium and transition state structure. The transition states have been, I will show you this, like you can see in this photo. This is a work done by one of my seniors. You can know about the transition state, like for the reaction mechanism. You can know about the dipole and quadrupole moment and polarizabilities. I will explain each point. If you don't understand any of the term in this lecture, you shouldn't worry about this, because we're going to explain each and every term. Vibrational frequencies, IR and Raman spectra can be explained in here, and NMR spectra, electronic excitation in UV spectrum, as I told you before, reaction rates, thermochemical data, protein calculation, that is called docking. So we will talk about all these things. Like the first few properties I studied, those are related to the DFT, and this last one, like I told you, the last one, which is protein calculation, the protein calculation, like we will do the docking thing. So I told you, like Amber and the Gold and MOE and Autodoc, these are the software which are used for the protein synthesis. Okay, in computational chemistry, I'm going to tell you about a general detail of the calculation. Like for example, there is you want to do a calculation. What you're going to do, the very first point is you will create a compound. Like I told you, the modeling, that teacher, he was coming, my school teacher, he was coming having that stick and those balls. He was using those stick and balls and was making that gas structure, and he was telling us the structure is like this. This is CH4, this is tetrahedral, because this is like this. Okay, he was telling like this. Then same work is done here in computational chemistry. You will create a gas of molecular structure, when you make this guess, then you will do the energy calculation math. So for energy calculation, you need energy calculation methods. So you will calculate the molecular energy. When you calculate the molecular energy, then there will be some of the property calculation methods, and you will use those one. Molecular structure, in the molecular, the property calculation, the first one you do is molecular structure, second is relative energies calculation, simulate spectra, mechanical properties, molecular dynamics, etc. This is just a general overview of your general detail of the calculation, what you do. Like this is this is the initial chart. You can know that how the calculations are done. In terms of calculations, nowadays, this is a nanotechnology and modeling simulation. From the very low level to a very high level you go, or you design a drug, or you want to study something in the atmosphere, you can do everything. Like we have done a lot of work on nanoscale, like the fullerenes, that is inorganic fullerenes. One of my papers that is in Journal of Molecular Liquid. My recent paper is in Journal of Molecular Liquid. The last part of this lecture is what is the scope or computational chemists, and what the computational chemists do. Keep remember, as I told you before too, that if you want to be a computational chemist, or you want to be a very good computational chemist, you must know about that specific field of chemistry. Like you should have hold on that computational chemistry field, and you should have also a hold on the computer software. If you don't know either of these two, you can't be a good computational chemist. For a good computational chemist, you must know about these two things. Okay, the first thing is the computational chemists, they develop computer models and simulations of chemical and biochemical processes and entities. So this is the first one. They perform and interpret statistical analysis of large database. They create usual representations like via Gauss view, and some other programs are also there. I think there is Gadro. This I told you about this Gauss view, and some others as well, like there is mole I guess, and some others as well, but mostly we use the Gauss view. So they create those visual representations of reaction pathways, so you can understand very easily, and molecular interactions, like how the molecules they interact with each other, and they also tell you other phenomena like about the electronic density. They told you about the polarity, dipole moment, etc., all those things. They collaborate with the laboratory researchers in industries, non-profit, government, and academic laboratories, like in different places in the laboratories the people work, so they collaborate with them, because if an experimental chemist or experimental scientist works, you collab with that chemist, you can do a very good work. Or the experimental chemist also needs a computational chemist to do work in an effective way. So therefore, this collaboration is very important. They characterize new compounds and processes to support patent claims. Like you want to claim that patent, therefore you need support. For that support, you need the computational chemist and to tell that this data is exactly the way he said this is. Okay, so help develop synthesis processes by identifying and characterizing reaction pathways and identifying the most likely products. So the reaction mechanism I told you, and I told you about how the reaction pathways are there, how the reaction will happen, how like there are different reaction mechanisms. You should understand this point as well. Like there are different reaction mechanisms, and there are different pathways for a reaction, but a computational chemist can tell you for the pathway which is easy with low energy and stable product, or stable way and easy way. So therefore, and they apply new software and hardware capabilities for data collection and analysis. The computational chemist, he can design of experiments, like he can design different experiments. These are the jobs the computational chemists do normally. Okay, there are many others as well. I'll make a separate video on this, that what is the application of the computational chemistry. But there are some of the challenges and some of the limitations the computational chemists and theoretical chemists both they face. Number first is on the theory level. The second one is on the software level and the computer program level, I mean, and the third one is the computer resource. Number first is theory level. Like the precision, is the precision high enough for the application? So you need a very good theory. Number second, the computer program, so you use different software. So the computer program you use is the efficiency and implementation of that program. And computer resources, like you need you need a specific computer for a calculation. So they definitely, is there any is there power in, sorry, is there enough power for the task? Okay, so these are the three challenges and limitations of the computational chemistry, and those are the things which are faced by a computational chemist. Okay, this was a quick lecture and overview of the computational chemistry, theoretical chemistry, experimental chemistry, the relationship of these two, what the experimental chemists do, sorry, the computational chemists do, how can they help out. So I told you that a computational chemist can help in any step, in every step with the experimental chemist. He can tell you before the calculation, he can tell you before the synthesis how that compound can be synthesized and can it be synthesized or not, like an entirely unknown compound. He can also assist in experimental data with you. He can also do the protein calculations, etc. So all these things are important. See you soon with a new video. Allah Hafiz.